Hello friends, welcome back to my YouTube channel. Today, uh, in this 42nd part of my discussion on distillation, I will continue discussing Lewis Sorel method. And in this particular video, I'll be discussing second numerical. I'm calling that as numerical number 2, that is based on the Lewis Sorel method. So in my previous video, where I solved one numerical by using the Lewis Sorel method, I discussed the graphical way of solving the numerical, the graphical way of finding the number of ideal or theoretical or equilibrium stages in a tray column. As you know, the Lewis Sorel method is used to find the number of ideal stages in a typical tray column. Now, in this particular video, where I'll be discussing numerical number 2, we will learn how to find the number of ideal stages if you have an equilibrium relationship available with you. So when you have the equilibrium relationship available with you, there is no need of plotting the graph. So there may be cases where you'll be provided with the equilibrium relationship, and then you should know how to use that to find the number of ideal stages in the tray column. So we are going to learn that in this particular video lecture. To begin with, let us look at the numerical statement. So you have a mixture of 33% mole of A and 67% mole of B. It is to be separated in a fractionating column. A is the more volatile component in the feed solution. The concentration of A in the distillate is 93% mole, and 96% of all A is in the distillate. The feed is half vapor and the reflux ratio is 4:1. How many equilibrium stages are required in each section of the column? And you can assume the average relative volatility to be 2.51. The Lewis Sorel method is to be used. So let me tell you, I have discussed this numerical in my earlier video, where I have used the McCabe-Thiele method to find the number of ideal stages. I'm giving link to that particular video in the description section. So at the end of this video, we are going to compare the results obtained with Lewis Sorel method with the results obtained with the McCabe-Thiele method. So you have a simple solution of two components, A and B. A is the more volatile component, and the contents of A and B in the feed that is given to us. Then the concentration of A in the distillate is 93% mole. So the concentration of A, percentage mole of A in the distillate is given to us. And one fact, what is the fact? 96% of all A that is present in the feed, it goes into the distillate. So we are going to use this information in our calculation. Then the type of the feed is given. In this case, they say that the feed is half vapor and a reflux ratio of 4:1 is to be used. And we are supposed to use an average value of the relative volatility, which is 2.51. So it is assumed to be constant, and for the constant relative volatility, we are going to use the equilibrium relationship to find the number of ideal stages. So this is a numerical statement. Now let us go and solve this numerical. Okay, first let us collect the given data. So you have the feed. Feed is a binary solution of A and B. There are two components, A and B. Out of this, A is the more volatile component. That is, A has a lower boiling point and a higher vapor pressure if you compare with B. And then the feed is containing 33% mole of A. That means XF is given to us, that is mole fraction of the more volatile component in the feed. We denote that by XF. So XF is given. XF is 33 by 100, which is 0.33. So this is how you can convert percent mole into fraction. What is the approach? Divide the percentage value with 100. You will get the mole fraction. So XF is 0.33. Then feed is half vapor. The type of the feed is given to us. And for half vapor, Q is 0.5. So you can understand Q as the fraction of liquid that is present in the liquid. This is another interpretation of the parameter Q. So in this case, Q is 0.5. We are not going to use this because we don't need Q in the Lewis Sorel method. But I have just noted over here. Feed being half vapor, value of Q is 0.5. Then the distillate. For distillate, what is given? You have the concentration of A is 93% mole. That means XD is given to us. So that is 93 by 100, which is 0.93. And other information is 96% of all A is in the distillate. And you'll shortly know how this information is used. Then the reflux ratio is given to us. It is 4:1. That is R is equal to 4. And then the average relative volatility is given. It is 2.51. And we denote that by alpha AB. And since this is an average value, I am denoting it as alpha AV average. It is 2.51. And what are we supposed to find? We are supposed to get the number of ideal stages by using the Lewis Sorel method. So based on all this information, we are going to use the Lewis Sorel method to find the number of ideal stages in the tray column to bring about this separation. Okay, now let us know how to solve the numerical solution to the numerical. First is, since we don't know what is the feed rate, so we are going to start with suitable bases. And in this case, the basis is F is equal to 100 kilomole per R. So we will do calculations for a basis of where the feed rate is assumed to be 100 kilomole per R. The first step is we will calculate dW and XW because all these three are not known and we need them in our solution. So first we will have to find these three quantities, dW and XW. And first we have this fact. What is the fact? 96% of all A is in the distillate. So how to represent it mathematically? How to show this mathematically? You can show it like this. So on the left hand side, it is product of XD into D. That is mole fraction of A in the distillate into the distillate molar flow rate. So that will give you moles of A in the distillate. And these are 96% of A that is present in the feed. So A present in the feed is given by this XF into XF. Fraction of A in the feed into total molar flow rate of the feed. And 96% of that feed is A. So A in the distillate, which is XD into D, is 96% of A in the feed, which is XF into F. Okay. So that means XD is known to us, it is 0.93. So it will be 0.93 into D. That is equal to 0.96 into 0.33. XF is given to us, it is 0.33 and F is 100. That means this information will give us the value of D. Because there is only one unknown quantity in the equation and that is D. And you can easily get that. So 0.93 into D, that is equal to 0.96 into 0.33 into 100. That is 0.93 into D. And the product of this three quantities is 31.68. That is D is equal to 31.68 divided by 0.93, which gives us D as 34.07 kilomole per R. So in this way, you get D. Next, we will use the steady state total material balance to get W. What is the steady state total material balance? F is equal to D plus W. That is, feed is equal to distillate, feed flow rate is equal to distillate flow rate plus bottom product flow rate. This is steady state material balance, where which is simply input is equal to output. So you have F is equal to D plus W. So F is known to us, it is 100. D is 34.07. We just calculated it and we are going to get W. So 100 is equal to 34.07 plus W. That is 100. So if I bring on this side, this will be 100 minus 34.07 is equal to W. That is, W is equal to, this subtraction will be 65.94 kilomole per hour. So in this way, you can get the bottom product. So you got D, you got W. Now let us get XW. And for that, we are going to use the steady state material balance for component A. So how it is written? It is F into XF, that is equal to D into XT plus W into XW. F is known to us, it is 100. XF is 0.33. D we found out, that is equal to 34.07 into 0.93 plus W we got over here 65.94, and we are going to get XW. That is 33 is equal to, so 100 into 0.33 is 33. 34.07 into 0.93 is 31.68. And then plus 65.94. 65.94 into XW. That is 33 minus 31.68 is equal to 65.94 XW. That is 1.3. The subtraction is 1.32. That is equal to 65.94. That is XW. 1.32 divided by the 65.94 will come on this side. So it will be 1.32 divided by 65.94. That is equal to XW, which gives us XW as 0.02. So in this way, this step is completed. We have got all the three quantities. We got D as 34.07 kilomole per hour. We got W as 65.94 kilomole per hour. And we got XW as 0.0. Okay, so after getting D, W and XW, next we will deal with the equilibrium relationship. And we are going to use this equilibrium relationship. Y is equal to alpha AB X divided by 1 plus alpha AB minus 1 into X. Alpha AB average, the average value of AB, alpha AB, we are going to use in this equation. So that is given to us, it is 2.51. This is alpha average, alpha AB average. So this is given to us, it is 2.51, and we are going to use that value in the equation. So it will be Y is equal to 2.51 into X divided by 1 plus 2.51 minus 1 into X. That is, Y is equal to 2.51 X divided by 1 plus 1.51 into X. So now alpha AB into X, that is 2.51 into X divided by 1 plus alpha AB, that is 2.51 minus 1 into X. So that is Y is equal to 2.51 X divided by 1 plus 2.51 minus 1 is 1.51. So the relation is Y is equal to 2.51 X divided by 1 plus 1.51 into X. But we need to have an equation where you can calculate the value of X if you know the value of Y. That means we want to put this equation in this form, X as some function of Y. And we are going to just rearrange this equation to get this form. So let us learn that. So what I will do, I will simplify this. I will bring the denominator on this side. So it will be Y into 1 plus 1.51 into X. That is equal to 2.51 into X. So I'll simplify on the left hand side. So Y into 1 is Y plus 1.51 into X into Y. That is equal to 2.51 X. In the next step, I collect all terms containing X on one side. So it will be Y is equal to 2.51 X minus 1.51 XY. And then I can take X common from these two terms. So it will be y is equal to x into 2.51 minus 1.51 into pi. And then finally, x will be pi upon 2.51 minus 1.51 into y. So you have got an equilibrium relationship of this form. So you have x on the left hand side, and on the right hand side you have some function of y. Because we will be calculating the value of x. If you remember, in the graphical method, we were getting x from the distribution diagram. You can just look at the video. Link is available in the description section. So the idea is to get an equation for x, so that if y is known to you, you can use that value of y and get the corresponding value for x. Now let us start with the rectifying section. The equation for operating line for the rectifying section, let me first erase this. The equation for the rectifying section line is yn plus 1 is equal to r upon r plus 1 into xn plus xd upon r plus 1. And how this equation is obtained, a separate video is available where I have discussed how to get the equation of operating line for the rectifying section. So we are going to use that equation. The equation is yn plus 1, that is equal to r upon r plus 1 into xi plus xd upon r plus 1. That means vapor phase, composition in the vapor phase leaving n plus 1th tray is related with composition in the liquid stream, that is leaving nth tray. Taken in the next step, we are going to use the values of r, xd. So r is 4 and xd is 0.93. So if you use those values, you'll be getting yn plus 1 is equal to 4 upon 4 plus 1 into xn plus 0.93 upon 4 plus 1, which gives us yn plus 1 is equal to 0.8 xn plus 0.186. So the equation for the operating line of the rectifying section is put into a simplified form by using the values of r and xd. And now we are going to use this equation and the equilibrium relationship. Here, instead of using the distribution diagram, we are going to use the equilibrium relationship. That is the difference. Let us move ahead. So let us start with the first stage, the topmost tray. So I can show over here. So you have the topmost tray. This is tray number 1, and vapor rising from tray number 1 will have composition of y1, and this vapor, they will be sent to the condenser where heat will be removed to get, just a minute, I'll show it properly so that you can understand it. So you have the top of the column, the first tray. Vapor rising from the first tray will have composition of yn, that is mole fraction y1, mole fraction of A in the vapor phase. Then same vapor will be taken to the condenser where they will be condensed, and then the resulting condensate, part of it will be sent back as a reflux, and it will have composition of xd. And then you have distillate, which will also have the composition of xd. So what is the understanding for first stage? Y1 is equal to xd. How this is possible, or how this is true, you can easily understand. You can refer my video on understanding the Lewis Sorel method, where I have explained why y1 comes to be xd by using the equation. Okay, now let us use this. For first stage, we are going to use this information. Y1 is equal to xd. So let us, I hope you have understood it. I am going to erase that. The only thing that you have to take from this particular diagram is y1 is equal to xd. So let us do that. So y1 is equal to xd. So therefore, y1 is 0.93 because xd is 0.93. So y1 is 0.93. And thus, if y1 is 0.93, we have to get x1. Now, how y1 and x1 are related? X1 is in equilibrium with y1. So, in order to get the equilibrium value for x, we need to use the equilibrium relationship. In our previous numerical, we were using the equilibrium diagram or the distribution diagram. Over here, we are going to use the equilibrium relationship. In simple words, we are going to calculate x for this value of y. So, x1 as per this equation will be equal to y1 upon 2.51 minus 1.51 into y1. That is, x1 is equal to 0.93 upon 2.51 minus 1.51 into 0.93. So, I have used the value of y1. And if I solve it, I am going to get x1 as 0.84. So, once you get x1, your calculations for first stage are completed. And for the remaining stages, we are going to follow the same steps. Okay, so after getting doing calculations for stage 1, now let us move ahead. So we are doing for rectifying section. The operating line is yn plus 1 is equal to 0.8 xn plus 0.186. Now let us do the calculations for second stage. So for second stage, the equation will be written as y2 is equal to 0.8 into x1 plus 0.8186. x1 we calculated, we got in the previous step, that is 0.84. So that will give us y2 as 0.8 into 0.84 plus 0.8186, which gives y2 as 0.86. Now x2 is calculated. We need to get value of x that is in equilibrium with y2, that is x2. So we need to use the equilibrium relationship. So x2 is equal to y2 upon 2.51 minus 1.51 into y2. Let us use the value of y2. So x2 will be equal to 0.86 divided by 2.51 minus 1.51 into 0.86. That gives us x2 as 0.71. Once you get the value of x2, calculations for second stage are completed. Now for the third stage. The operating line equation will be written in this way. y3 is equal to 0.8 into x2 plus 0.186. We got x2 0.71. So therefore y3 is equal to 0.8 into 0.71 plus 0.186. That gives us y3 as 0.75. Now we need to get x3, equilibrium value. For that, we are going to use the equilibrium relationship. So x3 is calculated as x3 is equal to y3 upon 2.51 minus 1.51 into y3. And that is x3 is equal to 0.75 divided by 2.51 minus 1.51 into 0.75. That gives us x3 as 0.55. That completes calculation for the third stage. Now fourth stage. For fourth stage, the operating line equation will be y4 is equal to 0.8 into x3 plus 0.186. That is y4 is equal to 0.8 into 0.55 plus 0.186. That gives us y4 as 0.62. Now let us get x4. And for that, we need to use the equilibrium relationship. x4 is equal to y4 divided by 2.51 minus 1.51 into y4. That is x4 is equal to 0.62 divided by 2.51 minus 1.51 into 0.62. And that gives us x4 as 0.4. So after getting the value of x4, our calculations for the fourth stage, they get completed. Okay, so after doing calculations for the fourth stage, we are going to proceed to the fifth stage. And for fifth stage, the equation will be written in this way. y5 is equal to 0.8 x4 plus 0.186. x4 we got previously, it is 0.4, and now we are going to use it. So y5 will be equal to 0.8 into 0.4 plus 0.186 after using the value of x4. That gives us y5 as 0.5. Then x5 will be calculated by using the equilibrium relationship. X5 will be Y5 upon 2.51 minus 1.5 into Y5. That is X5 comes out to be, after putting the value of Y5, it will be 0.5 divided by 2.51 minus 1.51 into 0.5, and that gives X5 as 0.29. So after getting X5, we now can see X5, which is 0.29, it is less than XF, 0.33. What is the meaning of this? The meaning is the fifth plate is the feed plate. On fifth plate, what is happening? The composition in the liquid phase is less than the feed composition for the first step. On the fourth plate, it was 0.4. X4 was 0.4. And now it has come down, it has become less than XF, 0.33. So this is enough to conclude that the fifth plate is the feed plate. So now, if we have to move further, we will have to move with the equation of the operating line for the stripping section. So stages in the rectifying section will be first 4 stages. First stage, second stage, third stage, and fourth stage. And then the fifth stage is the feed plate. So that completes our calculation for the rectifying section. Now we can declare that in this case, for this particular operation, the number of stages in the rectifying section are 4. First 4, 1, 2, 3, and 4. Now let us do calculations for the stripping section. And for that we will be using the equation for the operating line. The equation is ym plus 1 is equal to L bar m upon L bar m minus W into xm minus W upon L bar m minus W into xw. And now we are going to put the values for L bar m and W and then also xw, so that we will be getting equation for ym plus 1 in terms of xm. So after putting all those values, we will be getting an equation for ym plus 1, which will be function of xm. So let us do that. And for that, the information that is useful to us is the type of the feed or the nature of the feed. In this case, the feed is half vapor. That means 50% of the feed is liquid and the remaining 50% is vapor. That is, it is a partially vaporized feed. So if you have to look at the feed plate with this kind of feed, then you can see the feed plate. And now the feed, which is 50% liquid and 50% vapor, it is entering on the feed plate. The liquid part of the feed will be flowing down, whereas the vapor part of the feed will be joining the vapor stream. You have the reflux stream that is coming from the top. It will be joining the liquid part of the feed. And then you have the vapor stream that is coming from the stripping section. It is having a molar flow rate of G bar. And then it will be joining the vapor part of the feed. So the in the stripping section, the liquid in the stripping section will be combination of the liquid part of the feed and the reflux. So L bar is equal to L0 plus F in this case. Whereas G bar, and when in the rectifying section, the molar flow rate is G. So in that case, G bar will be addition of G will be addition of G bar and the vapor part of the feed. So this is how things will change when partially vaporized feed enters a typical tray column. A partially vaporized feed enters on the feed. Okay, so we were discussing about the stripping section. Or for the stripping section, the operating line is ym plus 1 is equal to L bar m upon L bar m minus W into xm minus W upon L bar m minus W into xw. And as the feed is half vapor, that is, it is a partially vaporized feed, you have this situation on the feed plate. And we are going to use this information to get the value of L bar M. And if you remember, we are even in the Lewis Sorel method, we are using one of the simplifying assumptions of the McCabe-Thiele method. And what is that assumption? Equimolar overflow and vaporization. And what is the meaning of that? Flow rate, liquid flow rate in the stripping section is same throughout. The liquid flow rate in the rectifying section and also in the stripping section, it is same, but at different values. So for example, in the rectifying section, L0, that is the reflux flow rate, is equal to liquid from the first plate is equal to liquid flow from the second plate, that is equal to liquid from the nth plate, equimolar overflow. And similarly for the rectifying stripping section, you have L bar 1 is equal to L bar 2, that is equal to L bar M, that is equal to L bar. That means in place of L bar M, I can simply write L bar. And this is due to the simplifying assumption of equimolar overflow. Same is the case for the vapor strip. G1 is equal to G2 is equal to G3, that is equal to G. And in the stripping section, you have G bar 1 is equal to G bar 2 is equal to G bar M is equal to G pi. So with this simplifying assumption, now you can write the equation for the operating line in this way. Ym plus 1 is equal to L bar upon L bar minus W into Xm minus W upon L bar minus W into Xw. Now our job is to get the values for L bar, and we already know the value of W and Xw. The main task is to get the value for L bar. So how are you going to do that? Let us understand. So if you look at the diagram, L bar is L dash plus L0, the liquid part of the feed, and the reflux liquid that is coming from the top. So L bar is equal to L0 plus L dash. And first we will have to get L0. For that we are going to use the definition of reflux ratio. R is L0 by D. L0 is equal to D into R. From this equation, D we calculated earlier. It is 34.07 kilomole per hour. R is 4, that is given to us. So if you use the values, L0 will be 34.07 into 4. That is L0 will be equal to 136.28 kilomole per hour. And L dash is the liquid part of the feed. And since it is half vapor, that is 50% of the liquid, 50% of the feed is liquid. So L dash is 0.5 times of F. 50% of F is L dash. So that is L dash is equal to 0.5 into 100. That is L dash is equal to 50 kilomole per hour. So we got L0, we got L dash, and now you can easily get L bar. So L bar will be equal to 136.28 plus 50. That is L bar is equal to 186.28 kilomole per hour. And we will be using this value and in the values of W and Xw in this equation to get a simplified equation for YF plus 1. Okay, so the calculations for the stripping section. The operating line equation is Ym plus 1 is equal to L bar upon L bar minus W into Xm minus W upon L bar minus W into Xw. L bar we got just now, it is 186.28, and then W we got earlier 65.94 kilomole per hour, and Xw was 0.02. So we are going to use these values in this equation. So it will be Ym plus 1 is equal to 186.28 divided by 186.28 minus 65.94 into Xm minus 65.94 divided by 186.28 minus 65.94 into 0.02. So that is Ym plus 1 will be equal to 1.55 Xm minus 0.011. So this is the equation of the stripping section line which we are going to use in our calculation. So this equation is obtained after considering the nature of the feed and what happens in the stripping section when the feed enters on the feed plate. So depending on that, we have converted, or we have got the equation for the stripping section line. And while doing calculations for the stripping section, we are going to use this equation. Okay, so we got the equation for the stripping section line. Operating line equation is ym plus 1 is equal to 1.55 xm minus 0.011. So now we are going to use this equation for our calculation for the sixth stage onwards, because you must remember fifth stage was the feed plate, and now sixth stage will be in the stripping section, and that's why we have to use this equation. So for sixth stage, the equation will be written as y6 is equal to 1.55 into x5 minus 0.011. x5 was obtained previously, it was 0.29. So therefore y6 is equal to 1.55 into 0.29 minus 0.011. That gives us y6 as 0.44. And then we are going to get x6 by using the equilibrium relationship. x6 is equal to y6 upon 2.51 minus 1.51 into y6. So after using the value of y6, you have x6 is equal to 0.44 divided by 2.51 minus 1.51 into 0.44. That gives x6 as 0.24. And then that after getting x6, our calculations for the sixth stage are completed. Now let us move on to the seventh stage. For seventh stage, the equation will be written as y7 is equal to 1.55 x6 minus 0.011. And after putting the value of xx, which we got earlier, so therefore y7 will be equal to 1.55 into 0.24 minus 0.011. That gives us y7 as 0.35. And then we are going to get x7 by using the equilibrium relationship. x7 will be equal to y7 divided by 2.51 minus 1.51 into y7. And y7 is 0.35, therefore x7 will be equal to 0.35 divided by 2.51 minus 1.51 into 0.35, and that gives us y7 as 0.18. So after getting the value of x7, our calculations for the seventh stage, they are completed. Okay, so after seventh stage, now let us do the calculations for eighth stage. For eighth stage, the equation will be written as y8 is equal to 1.55 into x7 minus 0.011. x7 was obtained previously, it is 0.18. So let us use this value. Therefore, y8 is equal to 1.55 into 0.18 minus 0.011. That gives us y8 as 0.27. Now we are going to get x8 by using the equilibrium relationship. So x8 is calculated as x8 is equal to y8 divided by 2.51 minus 1.51 into y8. So that is x8 is equal to 0.27 divided by 2.51 minus 1.51 into 0.27. That gives x8 as 0.13. And that completes our calculation for the eighth stage. Now let us look for the ninth stage. For ninth stage, the equation will be written as y9 is equal to 1.55 into x8 minus 0.011. That is y9 is equal to 1.55 into 0.13 minus 0.011. That is y9 is equal to, after you do this calculation, you are going to get y9 as 0.19. Now let us get x9, which we are going to get by using the equilibrium relationship. x9 is equal to y9 divided by 2.51 minus 1.51 into y9. That is x9 is equal to 0.19 divided by 2.51 minus 1.51 into 0.19, which gives us x9 as 0.08. Still we have not reached xw, which is 0.02. So on the ninth stage, the liquid leaving the ninth stage will have a composition of 0.08. That completes our calculation for the ninth stage. So after ninth stage, let us look at the 10th stage. Equation for 10 stage is Y10 is equal to 1.55 into X9 minus 0.011. And X9 we got previously, it is 0.08. Let us use this value. So Y10 will be equal to 1.55 into 0.08 minus 0.011. That gives us Y10 as 0.12. Now let us get X10. For that we need to use the equilibrium relationship. So X10 is Y10 divided by 2.51 minus 1.51 into Y10. That is X10 is equal to 0.12 divided by 2.51 minus 1.51 into 0.12. 0.12 divided by 2.51 minus 1.51 into 0.12. That gives us X10 as 0.05. Now the 11th stage. For 11th stage, you have this equation Y11 is equal to 1.55 X10 minus 0.011. X10 is 0.05. So therefore Y11 is equal to 1.55 into 0.05 minus 0.011. That gives us Y11 as 0.07. Now let us get X11 by using the equilibrium relationship. That is X11 is equal to Y11 divided by 2.51 minus 1.51 into Y11. That is X11 is equal to 0.07 divided by 2.51 minus 1.51 into 0.07. That gives us X11 as 0.03. Still, we have not reached XW, which is 0.02. So maybe on the 12th stage, this is going to happen. So let us check it. So after getting X11, our calculations for the 11th stage, they are completed. Now let us do the calculations for 12th stage. For this, the equation will be Y12 is equal to 1.55 X11 minus 0.011. That is, and X11 or X11 we got just now 0.03. So let us use this value. So Y12 is equal to 1.55 into 0.03, that minus 0.011. That gives us Y12 as 0.03. And now let us get X12 by using the equilibrium relationship. X12 is equal to Y12 divided by 2.51 minus 1.51 into Y12. That is X12 is equal to 0.03 divided by 2.51 minus 1.51 into 0.03. That is X12 is equal to 0.01, which is equal to XW. And the condition is you have to go on doing the calculations for the steering section till X becomes either equal to XW or less than XW. So now here it is equal to XW. That means we have reached the reboiler. The 12th stage is actually the reboiler, where composition is equal to XW. So that means X12, which is 0.01, it is equal to XW. Thus, the 12th stage is the reboiler, because in the reboiler, composition is XW. And therefore, how many stages? What are the stages in the stripping section? 5th is the feed plate, then 6th, 7th, 8th, 9th, 10th and 11th stages. They are in the stripping section. First 4 stages, 1st, 2nd, 3rd and 4th, they were in the rectifying section. 5th was the feed plate, and 6th onwards, 6th, 7th, 8th, 9th, 10th and 11th stages, they are in the stripping section. So if you have to summarize the result, number of theoretical stages is, or ideal stages, it is 11 plus 1 reboiler. And out of this 11 stages in rectifying section are 4 and stages in the stripping section are 6, whereas the feed plate is 5th plate. 5th stage is the feed plate. And quickly, if I compare these results with the results obtained with the McCabe-Thiele method, you can check we got the same number of ideal stages. Ni is equal to 11 plus 1 reboiler. But McCabe-Thiele gave 5 stages in the rectifying section and 6 stages in the stripping section. So number of stages in the stripping section you are getting same with the Lewis Sorel method and the McCabe-Thiele method. But the feed plate, as per McCabe-Thiele method, it is 6th plate. So these are the results that were obtained when the numerical was solved by using McCabe-Thiele method. And now over here we have got a result with the Lewis Sorel method. So solution by using McCabe-Thiele method, I am giving link to that video. So you can just watch that video and compare how the methods they are applied for solving such numericals. So with this, we have completed the solution. We have got the end result. We have reported the number of stages, total number of stages in the reboiler, rectifying section, stages in the stripping section, and the number of feed plate. So with this, I complete my discussion for this particular numerical. So thanks for watching my video. I hope you have learned something. If you have any doubt, if you have any questions, you please mention them in the comment section. Do subscribe to my channel. Tell your friends to subscribe to it. And I'm sure you'll join me in my next video lecture on another topic in chemical engineering. For now, thank you. Have a nice day. Bye bye.